Okay. Makeup exam, I think that I got confirmation it will be tomorrow at 12 and it will be at 737, not where I said originally, which is tiny room, in this side, in the north side, the room that if you go in this corridor, all the way to that. That's probably. Right now I have, yeah, I'll publish it. Anyhow, one of the room in this floor. So that was a cute question from the exam, so let's burn it. UVW, 3 vectors that forms an orthonormal basis. And I take the first one, to be precise, I take the Euclidean coordinates of the first one and make a row of a matrix out of it. And similarly for V and similarly for W. And I created this matrix and I want you to tell me how do you know that this matrix has an inverse. I mean, in general it would have been maybe a linear algebra question, but somehow it's very related to this course, so it's much more. Everybody understands what am I asking about? Yeah, and you suggest to?
So because it's composed of orthonormal vectors, that means that A is a unitary matrix. So any unitary matrix, its inverse will be equal to its transpose. So you just flip UV and W from being the rows to being the columns, and that's the inverse of A.
So you didn't talk about unitary matrix and some other words that you said that you didn't discuss in this course, and I need to remind yourself what you meant, but the suffix of your answer was perfectly good. But how are we proving that it has a matrix, that it has an inverse? Let's generate the inverse directly. Namely, here is A, U, V, W, and as we discussed numerous times in the course, if I take U and make it a column, and same with V, and same with W, and now I multiply these two matrices. And what do I get? It's index 1, 1. I have U dot product U. What is for every vector X vector, you know that the length of X is nothing but X dot product with itself, all of its square root. Yeah, by the way. But if this is 1, then square root doesn't matter, and that's just a length of X. So for U that has a unit length, dot product U, put it 1 over here. U dot product V will be 0 because they are orthogonal, and similarly for U dot product W. And V times U will be 0, 1, 0, and 0, 0, 1. So we just prove its existence by building it directly. This is the inverse. And we talked about it many times because, said many times, you need to rotate from one coordinate system to another, generate the three vectors. We saw it in the case of the billboard. You have a billboard, you want to align it with x, y, z. You are generating with the billboard one vector that fits the bottom side of the billboard, one side hits the vertical side, creates a normal, and that forms your rotational matrix. That's it. Said many times. So if you are rotational from one coordinate system to another, it's just multiplied by the unit vector, the orthogonal basis of this other world. And going back, you're just, you need the inverse of the matrix, but the inverse is just a transpose. Just switch columns and rows. Anything else from the midterms that you want me to chat about? Okay. Question between Goard and Phong interpolation. Which one is better to capture specular reflection? Easy question, but let's remind ourselves. Goard versus Phong. Goard says they both start by computing the approximated normals, n1 prime and n2 prime. N1 prime is the average in the corner of the actual normals, and 2 prime is the average of these normals, and 1 prime is the average of these normals, normalized to be of unit length. And then we are computing the intensity, the shading at V1, and don't want V, yeah, at P1 and P2, yeah, V for vertex, not for vector. We compute the colors, including all the effects at P1 and P2, and now the difference between the Goard and Phong starts to be relevant.
I asked you for help. I would have done it.
Can you go over the perspective projection problem number 2? It was like something with 1, 0, and there's a. I remember what it looks like. I don't remember.
Oh, okay, I'll check it at the end of the class. So we compute the approximated normal, that's a common. What Goard says, let's compute the color here, let's compute the color plus shading plus lighting, everything. But at the two vertices, and now interpolate the colors along the face, along the segment in 2D, along the triangle in 3D. Phong interpolation model, to be not to be confused with Phong specular simulation. Phong interpolation model says compute for every point its approximated normal, so there is a different normal for each point, and use this normal to calculate the shading at this particular point. So more expensive, of course. You have to now average, do linear interpolation of vectors instead of just RGB. It's vectors. You need now to divide it because you want a normal vector division. And then for each point, you need to run the whole mechanism of the shading interpolation. But, of course, why is this especially important for specular reflection? Because if the sun is here and the viewer is here, then there is a specular spot right here at the middle only. Right, this is a perfect mirror. The center of the specular spot would be in the point where the viewer sees the sun with the very same angle. But since it didn't happen neither in V2 nor at V1, then when I interpolate between them, I will not get the interpolate spot either. Do you remember the question by heart? Or do you need to?
I don't know by heart.
Which one?
Number 2.
Sure.
How did you do it?
I didn't do that one.
You did that one?
I think I can skip that one.
So you need to pick to identify where is P prime. P prime will be, P prime is where the camera sees P. But when we generate the image, if you think about the image plane as a window for a second, and in this window we see the 3D world that happens here. Now, where on the window, on the ij pixels of the window, I will see P. So, draw a straight line segment from P to the camera and ask where is this line segment intersect the image plane. There's a projection. So Z equals -1, and then to compute the intersection point, you are using triangle congruency. Similarly, congruency. That this divided by this equals P prime over here divided by D, by -1. And that's all. So you're doing it for X, you're doing it for Y. And the Z value of this point P prime is just -1. So that gives you the relationship. And now you're moving. So what did we get? I might be wrong about the plus minus, but Y divided by Z equals Y prime, well, P prime is divided by this distance, 1. Well, in general, it will be this distance D, the distance to the image plane, from which we are moving D to the other side, and we got Y prime. And for X prime, it's exactly the same thing. But the trickier part was to express it as a matrix. That's where we heavily needed the homogeneous coordinates to express the same process. But just as a formula, which is what I asked, you're just using triangle similarities. Okay, let's talk about hashing. Hashing, you have a set of keys, K1, Kn, and are keys in general, and you have a hash table, and age, which is a hash function, takes one of these keys, ki, and pushes it to one of the cells in the hash table. We assume that in my hash table, I have a fixed number of cells, usually from 0 to m minus 1, it's m cells, and the hash function takes a key and spits out a number. And usually it will try to do it in somehow a fair way. So every key has the same chance to fall into every cell. Like that for 2 keys, I'll have a relatively linear small chance that these 2 keys will fall into the same cell. But so age of ki is a number that maps ki for this cell. And I'll put ki in this cell, and it helps for insert when you're using it. For inserting point, you take the first key, compute its hash function. For example, take the number of this key, k1 equals 35792. You'll say that m equals 100, and I'll use the last 2 digits as a hash function. That is a hash function. Age of k is k mod 100. Just isolate the last 2 decimal digits. And that determines at which cell I'm placing this point. Now, it could be, of course, like every hash, it's very unlikely that if n the number of keys and m the number of cells are roughly the same order of magnitude, it's really unlikely that every cell will contain only 1 key. Even if you have excellent hash function, and even if things are distributed, are very nicely distributed, it will be unlikely that I have many keys that are mapped to the same cell. That's as far as realistically you should keep your expectation. You will not have more than 10 keys that falls into the same cell. But occlusion always occurs, unless the number of cells are about quadratic, like n squared many cells and only n keys. But that's ridiculous amount of memory where almost all of it is unused. So there are some collisions, and then hash tables have a few strategies to handle collisions. 2 famous ones is if I have collisions, if I have both ki and kj mapped into cell number 1, I'll keep them in a linked list. All the keys that are mapped into cell 1, I'll keep them into k list. So if right now I'm inserting the number 3301, what do? I take its hash function, if that's my hash function, take the the two least significant digits of the key, go to the table, find in the table where is a linked list that this cell corresponds to, go, say, to the end of the list, and insert 3301 at the end of this list. Now, that was the insert process. It doesn't make much sense to only insert data into the hash table. Probably I want to retrieve it, to ask, does 3301 is a key that you ever stored? And if you did, then maybe there are auxiliary data associated with this. Like if it's a point in 3D, then its triangle, there is some color associated with this, vertices, attributes. How does the find of the key works? find 3301. How it works? Compute the same hash function. You don't change your hash function. It's how you find things. What does it tell you? It's 101. So if indeed, at this point we have no clue if 3301 exists, but if it is, we don't need to look for, or among all the values, all the keys in the table, we just need to look at values on this linked list versus other keys that I didn't show you yet that are over here, and they are all of cells 0, 1, 2, 3, all these cells. We don't need to check if 3301 is there. We just need to check among the cells that are pointed by the hash table, by the cell whose index is what the hash value is. So that's the simpler but less practical methods to solve collision. Use linked list. There is also open addressing that says everything will be in the table. If a cell is occupied, then I'll just check the next cell. Maybe the next cell is free. And if the next cell is free, then maybe I'll check the next one and the next one, the next one, until I'll find a free cell. And when I'm doing the find, I'll just do the reverse process. I know where I start my search. That's a very simple open addressing method. And on top of it, there are better open addressing methods that says maybe if a cell is occupied, I don't necessarily go check the next one. I'll actually have another hash function that tells me by how much to jump. Or I'll check the first, then the second, then fourth things. I'll do change by squares of my trial number. And it goes on and on about other methods to use open addressing. And practically it works much faster because linked list and pointers are not very efficient and don't handle well moving from one storage media to the other. Like SSD versus a cache doesn't handle well upload, download, and all array. Array sits contiguously in your memory and very nicely to shift the whole array with all the keys inside. So open addressing is much faster in general. Any questions so far? Just a reminder from courses that you've hopefully seen probably multiple times. Now, I'm probably saving my place in heaven. I'm the only one that keep doing. Another example of a better hash function. What's wrong with my hash function right here, right there? Assume that my keys are my keys are 30, 50, 90, 20, 200, and that's a hash function that I'm using. And I'm just using the last digit as a control number first to indicate that it's an item from this class. What's wrong with this? That out of all the cells in the hash table, only the one that has divided by 10 will ever have a key. If the data has some simple structure, the performances of the hash table will be bad. What does it mean? Does it mean that I cannot find this key? No, I can still perform insert and will find and can still perform find, but out of all the cells, the 100 cells that I created, only 10 of them will be non-empty. And on the other hand, for one such value, I'll have to check a very long list until I'll find what I'm looking for, declare that this guy doesn't exist in my list yet.
So it's a high collision rate, so you said you want to mod by a prime number.
Prime number is one solution. Do the mod by prime number, but it's good and bad. It's nice that I'll pick the size as a power of 2. Your memory likes you. Power of 2 as 1 megabyte, gigabyte, and so on. But then points will have the same performance, except that now it's not the factor of 10. It's point that you only look at the binary representation and only look at the few last bits in the binary representation. So it's exactly the same problem, just in binary instead of decimal. But yeah, if you don't know better, getting away, don't pick 100 or mod 10 as your hash function in terms. Pick M to be a prime, which is good for many reasons, and then your chances of too many collisions decreases significantly. And I want to show another method that doesn't contradict picking them to be doesn't. Well, it's a good idea to, as we said, pick M as prime. Good for some things, bad for another. Like computing modulo 2 to the M is also very fast, because then you're doing just bitwise XOR. But you have a mask that says out of all the number, I'm only looking at the last R bit. So it's very quick, but runs into chance of collision. So picking M as is prime is one good idea. And in addition, instead of doing age of K equals K mod M, instead of this, I'll do AK mod M, where A is a constant. And it goes on and on about what are good constants. You want the constants that look strange. Square root 2 is a nice one. 10 is a bad one. Okay, so you first multiply by a strange constant. Just throwing a number. The stranger the number is, the better it is in terms of hashing. People that took courses with me don't answer. The source of the word hashing is why do we call it hashing? Nobody? Why are we calling hash functions? We're taking the data, and what do we do to hash potatoes? We're taking the data, we chop it, we scramble it. That's exactly what we want to do with the keys. We want to take whatever was the original structure of the data and scramble it and now drop the keys, and hopefully the distribution of these keys is just as if we picked for every key a random place, independent of other ones. Now, of course, we don't pick for every key a place at random, because then we will never be able to find it, at least not efficiently. But when we look at how keys are distributed between the cells, we want them to look like it is a random scrambling thing. That for every key, the chance to fall in each one of the cells should be roughly 1 over n, the number of cells. Equal chance to fall in each one of them. So this constant is good. And then your hash function takes a constant and multiply by this one. Multiply, you have a new key k, multiply by a. Now you have a huge number, and then do modulo m as before, just to get a number that is between 0 and n minus 1, a legit index. Now, what if the key has two parts? For example, we are talking about geometric hashing. So these keys are going to be, for example, points that have the x coordinate and y coordinate. And what we can do if x and y, if the x coordinate and the y coordinates are integers, both are int, what we are going to do is similar to take the hash function multiplied by a, except that we will have two constants. We will use two constants, a1, a2, and age of k is, take the first constant, a1, multiply by the x coordinate of k, plus the second constant times k dot y. So now that's the x part of k multiplied by a1. That's the second, the y part of k multiplied by a2. And end up by doing and the last thing, what do I do with this number? If I want a hash function, I need an index in the hash table. So I will beloved modulo n. And now I have something that can take points and hash them. At least points, as long as it has integer coordinates, I can hash points. Well, only if I hash coordinates, and still what do I get by it? So let's start to see where it's leading. So here are points that lives in 2D or 3D, like vertices of triangles. And I want to be able, in my computer games, to know who are the players near me, which there are lots of data structures, but and I don't want necessarily to only know the unique closest to me, but I need a good filtering. The highlight here is filtering process that will give me just ones that have good chance that are near me. So where does it lead? We decide about a I decided about delta, some numbers that I think that more than delta is probably too far away for me to be relevant for a point, and less than delta is, I'll think about it as close, or Interesting clause. Delta would be 1 mile. And I'm going to build a grid, and I need to tell you what do I mean by building this grid. Like, building the grid doesn't mean that I need to draw each line individually or need to store all these lines individually. To know about this grid, all I need to know is decide about a point 0, 0, 0, 0, 0 in 3D, and you know what is delta, and that's it, because now this corner has a coordinate delta, delta. This point has a coordinate of 2 delta of x and delta in y for this point. And this would be what? 0, 1, 2, 3. So 3 delta and 0, 1, 2 delta. So to know about this grid, all you need to know is where is 0, 0 and what is delta. So what is common to the x, y coordinates of everybody inside this cell? Everybody inside this cell, all these points, what can I say about the x and y?
If you take the floor of x and y, they'll land
So,
at the bottom left.
That will be in the exactly one line from here. So x would be between, for this cell, would be between 0, 1, 2, 3. So x here is larger or equal than 3 delta, because that's 3 delta, but smaller than 4 delta. And y is between 0 and 1 delta. Agree? That's common to all these points. And all these points will have the same x, except that y is between 1 delta and 2 deltas. If you don't want for ambiguity between the points, then let's say that this side is smaller or equal and this side is strictly smaller. So now every point is strictly is belonging to only one cell. So each and every point, each and every player that lies inside this cell, all the pi's over here, its x and y coordinates satisfy this condition. If it's inside this grid cell, which means, which happens if and only if x divided by delta floor would be x divided by delta floor is 3, and y divided by delta floor again would be 0. Now, what's the operation that I want in my computer again? I just teleported into this cell, and I want to know who are the players that are near me. So I'm going to check the cells that I'm in, and maybe I'll check also the nearby cells if I want to be sure. But what is the data structure that I'm going to use? The geometric hashing that we have right here. Every player that I have already, for each such player, each such point, for every player, pi, for every player, pi, I'll compute the age of pi. I'll compute the hash function of the location of this player to be a1 times pix, the x coordinate of pi divided by delta. A1 times pix divided by delta plus A2 flow of pi dot y divided by delta. And as usual, mod m. Two players in the same cell will have the same hash function, which means that I can retrieve them from the hash table very efficiently by just one lookup into the hash table. But I have my new player. Q was just teleported or joined the game, and that's the location of Q. Who is the players in the same, well, Q here doesn't have anybody, here is P7. How do I know that P7 is close to the query point Q? Because for P7, I already hashed it, I stored it in the hash table with the x coordinates based on this formula. So it has this key. And now Q does the same process with the x and y, and it got the same hash value as P7, so it can find it in constant time in the hash table. Extremely useful. Now you have a hash function that in constant time can tell you all the points that I think that are close to me. Here is how I find them. It's my cell, maybe it's a nearby cell, but Q says, so P1, what's the distance from Q to P1? P1 is not in a cell, P1 is not in the cell of Q, and P1 is not even in a cell that is neighboring the cell of Q. Between P1 and Q, there is distance of at least delta, at least 1 mile. So in our axioms, we decided that more than a mile is not relevant, too large. I don't care about it, at least not for now. Cool, geometric caching, very useful though. Of course, it's not, you can make it more complicated and you are losing some of the simplicity of the program. You can say in some region it will be more refined, in some region it will be less refined. Definitely doable, definitely common. But and now this is a data structure that if you have a lot of small triangles and you want to use a Z buffer from some point, and I want to start feeding, remember you're feeding the triangles, you decide about the order that to the Z buffer you feed the triangle. You want to start from triangles that are near you, and maybe that will block your view completely. How do I find triangles that are near me? And again, it's not a bad thing if I put a triangle that is not relevant. But I don't want to waste too much time with triangles that are too far away unless I see that my vision around me doesn't cover everything and I want to explore further away triangle. As long as my triangle is small, put all the vertices in a grid, and as long as the size of the grid is larger than every triangle, you have a fantastic time that only the relevant triangles will be fed once you have the viewer. Okay, don't take my word. Google ChatGPT for geometric caching. Really, really useful, as well as face recognition, as well as protein docking. Yeah. Taking shapes and assigning for each one of them a hash value. Okay. Accelerating data structure, binary space partition. We had these slides already. Just tree that builds on triangles. The term BSP is very generic. There's lots of types of BSP. So one application for it for the painter algorithm, but we can build many types of BSP. We will go back to the notion of BSP later, but quad tree will be one type that can produce BSP. So quad tree, one of my favorite data structure, very simple data structure that likes geometric objects, for example, points, houses, pixels, 3D things, and can tell you quickly what's happening in some vicinity, some neighborhood of the world, some region of the world. So to describe quad tree, and these slides you've seen it in computational geometry with almost no modification. Let's define quad tree. So quad tree can be built on lots of types of data. To introduce it, I'll use very simple data, namely, I have an image with pixels, and every pixel is either green or red. I needed colors that I can also draw with markers, so either green or red. So that's the only value of the pixels right now in this example. And I make one more assumption. I'll say that the size of the image is maybe it's 4 by 4 or 8 by 8 or 1024 times 1024. That is number of rows is a power of 2 to the h for some number h, and so is the number of columns. You'll see in a second why I'd like it to be the size of the image. Maybe you want to pad the image with some empty blocks until you're getting to this size. Okay. And now I want a data structure describes that can help me do ray shooting fast, ray tracing fast, or to know what's in my vicinity fast. So, and what we can have many other applications, like for a given query point Q, did I fall in a red or a blue? Here is my query point, did I fall on the green or red? Quad tree is overkilling this query by itself. I can solve in other ways. But here is a more interesting query. And when I'm in query, I want to say it's not, the query is a disk, and I want to ask, are all the pixels in the query are all red or all green or mixture of the both? For the query point disk, what do I mean by the query? Well, it's the term query that we'll use a lot in our next meeting. It's if I just have one disk in the world and I have all my data and I need to answer this query only once, I can check each pixel individually. I wouldn't waste my time with a quad tree. The deal is that there is a lot of ray shooting that I'm doing in other application, or a lot of queries with lots of different disks that I'm doing. And since there are so many queries, it pays off to spend some time in the pre-processing, namely build your data structure, and this time will pays off in runtime, especially if it's interactive runtime, interactive video game, that you'll have a lot of such queries, and for each such, and the time that you spend for building the data structure, like the quad tree, this time will pays off because the time for answering each such query will be much faster than checking each pixel individually. Okay, so a query here, where is the center of the disk, how large the radius of the disk, another type of queries, or how many green points there are in the disk, and so on and so forth. Types of queries, another disk that contains both red and green. So, how do I build a quad tree? I can start from the leaves, or I can start from the root. Conceptually, let's start from the root. Now, the root has some region that is associated with this, as well as every other node. Every node has its kingdom, has a region in the plane that it corresponds to, owns it. And so for every node V, the node V has some region R of V, R for region. That's geometric part that it belongs to. In 2D, it will be quad 3. In 3D, by the way, it will be even more important and more popular data structure, and it will be called oct 3, for reasons we'll see soon. But I'll describe it in 2D. So I'm going to the root, and the region of the root is the whole image. And in some cases, the root will also be the only leaf. That is, the root will not have any children. How do I decide? I'm asking the root, hey, is the region that you're in charge of, which is in this case the whole image, is the whole region monochromatic? Is this fully green or fully red? And in this case, the answer is no, it's not fully chromatic. My region has both red pixel and green. The rules of the quadtree says, in this case, you split the region into 4 quads. Where do you split them? Exactly in the middle. So had my quadtree be constructed on 0, 1, 2, 3, 0, 1, 2, 3, where I split it so each quadrant has exactly the same edge length. It is different than data structures that we'll see, like R trees or KD trees that tries to balancing, mostly KD trees, tries to balancing, so it has the same amount of data here. Quadtree doesn't care about it. Quadtree will say, I look at my coordinates between 0 and 2 to the m, between 0 and 2 to the h minus 1, I'll pick the middle. And that's why it's convenient that it's power of 2, because I can always split it. And it's all integers. So I have my 4 quadrants. The northwest, northeast, southwest, southeast. Also, I'll call them quadrants 0, 1, 2, 3. And they correspond to 4 children of the root. So the root that started as a leaf now has 4 children. Each one corresponds to a quad in the quadtree. How did I create this quad? I split them once by x and then once by y. If it was in 3D, I would split by x, by y, and by z, which would mean that from one box, I would create 8 boxes. Make sense? Split by x, double by 2, split by y, double by 2, split by z, double by 2. So if I have 8 children, that's why it's oct 3 in 3. So here are the 4 children, each one with its own quad. Here is a child of the northwest quadrant, quadrant 0. And I repeat the very same question. Hey node, what is your region? It says, this node, that's my region. Is your region monochromatic? Quadrant 0 says yes, absolutely. So I don't see any reasons to split this quadrant. Instead, I'll just keep on the leaf. It is left as a leaf. And as a leaf, it has a label that just tells me all the points in my region are green. That's this green label over here. Quadrant 2, southwest, all the region in me are red. So I'm not splitting you. I just need to keep this label in the leaf. Southeast, all of it is green. What about the northwest? It's not monochromatic in this quadrant. So we split it according to the very same rule. split into 4 equal size quadrants, as so. And do for each one the same thing. Quadrant 1,3, it's not 13, it's 1,3, fully red, don't need to split it. 1, 0, don't need to split, 1, 1, don't need to split, and 1, 2 is not monochromatic, so I need to split it once again into 4 equal size quadrants, 1 to 2, 1 to 3, and so on. And at this point, each one is a pixel, and I don't need to split it anymore. What's the height of the tree? How high can it be? Well, if I started when it's 8, and I go all the way down, I can split it at most 3 times. 8 on the x, 8 on the y. If I started when the x direction is 2 to the h, then at each iteration, I go back 2 to the h, I split it by 2, now it's 2 to the h minus 1, 2 to the h minus 2. After h many steps, at most h many steps, you're down to individual pixels. But what's the beauty? This quadrant doesn't have any obligation to be balanced. It's not a balanced tree and not even trying to. It's the opposite. It says, if nothing interesting happens here, there is very few data, I don't need to split. I don't need any further refinement. I'll keep myself as a very large part. And if you have any query that is in the northwest region, you'll get your answer very quickly, and it's a huge region. But the same goes for the southwest. This 1-1 region is also quite close to the tree. So yeah, it has some height, but it's not a huge height. Right? And in most cases, you don't even need to visit so many nodes. Okay, so that's how we conceptually built the tree. So we can build it from the root down. We just need to know at each moment, do we have both colors or just one color? Or we can start with individual pixels and merge them. If we say that I have 4 pixels, these 4 pixels realize that they are all of the same color, then they'll be merged. I wouldn't keep them as leaves. I'll keep them as a node maybe of size 2 by 2. And then as a 2 by 2 node, I'll check my siblings that are also 2 by 2. If we all have the same color, then we are replaced by a common parent. Yeah.
Realistically, we're not going to just be given red or green. So is it going to be determined if it's monochromatic or not based on the amount of
That's a toy example just to explain quadries.
Yeah, but in a realistic scenario, are we just going to be saying if there's 2 objects in here that we need to split again?
Yeah, okay. Exactly. You have some number, as long as this number is small. Don't split it. If the number is beyond your taste of good taste, then split it. But splitting is always in the middle. Why always in the middle? Because it takes 15 minutes to program the whole quad. It's so simple. There is lots and lots of tricks that make the search here much faster than in other trees. You don't necessarily even have the pointers. You don't really have to have the dynamic allocation. And you can do point location very fast by just checking 1 bit at a time. We talk about it. Okay, oak tree, once again, you're just splitting by 8. Same idea. And again, not trying to be balanced. How high can the tree be? I think United States, say 4,000 miles, make it go down to 1 inch. How many levels do you have? 20, 30? From going from 4,000 miles to 1 inch. 20, 30 levels at most until you're down to this level because you shrink it exponentially. Okay, point location. I have a point, that's the simplest query. I give you a point, x, y. How do I know if this point is green or red? Let's go with it. I have a point x, y. How do I know if hue is green or red? I start at the root. I'm asking, is Q in the region of the root? Yes, it is, in this case. If Q is here, it's not. If Q is here, it's in the region of the root. Great, I'm asking the root, hey root, are you a leaf? The root is not a leaf. Okay, then the root pushes the problem to all its 4 children. The root doesn't even try to navigate or to steer the query. The root just says, I was not able to give the answer when I have my point Q, then I'm going to check each one of my subtrees, my immediate children, with the same query. Here is my finger here at Q, asking, are you in the northwest region? No. No. Are you in the southwest? No. Are you in southeast? Yes. Are you a leaf? Yes. And all is green, so I can answer the query. Okay, so I just need to go down until I find the leaf that contains Q. By the way, with a bit more tricks, with hashing, you can do the whole point location. What did we say the height of the tree? The height of the tree at most is, if this is, we said 2 to the h times 2 to the h, many pixels, so that's a resolution. What's the time for the point location? This is h, help. Or if I have n pixels inside it, let's say that there are n pixels. So what is the height? At most. It could be much less. It could be a leaf that has, the root could be the leaf, but at max, h, right? The height is h, which is roughly log 2 of n, and point locations that we just saw naively takes h, the height of the tree, with a bit more tricks. It takes log h, which is log of n. So it's really, really fast. Okay. You can store at each node what is its range by, say, computing the lower left and the upper right corner. Essentially, you don't have to do it because you know where did you start at the root, and then you know at each time, did they go left, did they go right. So I know I can keep track as I'm going down the tree from the root to a leaf. I can always know at what is the region of the node I'm visiting. So useful to store this for coordinates. If you want, you don't have to. You can always reconstruct it. Okay, more realistic objects, points. Now I have a set of points. What I need to come up with a splitting policy. In the slides, splitting policy would be split a quadrant if it has more than one data point. Split a quadrant if it was more than one data point. So the root says, do you have only one data point? No, I have about 6 of them, namely A, B, C, D, E, about 5. So I'm splitting once again in the middle of the world, independent of the data. Quadrant 0, northwest. Do you have only one point? Yes, only A. So the quadrant now, this quadrant stays as a leaf, but this leaf needs to know that it stores A. I don't know where is A in the quadrant. It's a data point that can be anywhere in this quadrant. So I need to store its exact coordinates, all the attributes that are associated with this data point. Make sense? Everybody understand why I have to store this node A with all its glory, a pointer of where do the point is stored. Quadrant 3, only one data point, namely D, stored. quadrant 2, empty, that's fine. Leave it as an empty quadrant. And quadrant 1 that has 3 points inside it needs to be split, as usual, at the middle. Okay, and once again, if it's all integers, then after a while, after you got to a single pixel, that's a minimum size that you're doing. In general, the size of the quadrant is like what's the maximum ratio between the furthest away point to the 2 points that are closest away, that if they have rational coordinates. Now, as you asked, the 1 point per quadrant is easy, but I might as well say, as long as I have less than 17 points in a quadrant, I don't split it. If it's more than 17, then I do. Whatever I can, you'll see next why do I care about it. So how do I say find all the points inside the query disk? I'm asking, I gave you a query disk. I want to know all the points inside the query disk. Now, looking at a region ROV, the region of a node, and the query disks, there are a few options to the relationship between them. It could be that ROV is completely disjoint from the disk, the query. I want to know all the points inside the query. I look at node V, whose region is fully outside, no points in common. And in this case, of course, no points in ROV, no points that are stored in the node V are also in the query region. Query is like, I think about building a Walmart right here. Who lives 5 miles away from me? That determines what. One option, Q and ROV are disjoint. Another option is ROV for some node V, the region, say, of the root, is fully inside the query disk. The query disk contains the whole image, the whole data, and then of course every point in the tree or every point in the subtree of V is inside the query disk, and I don't need to even check any further in the subtree. Everybody in V is inside Q, no questions asked. Third case, Q and ROV overlap, but ROV is not fully inside Q. They have some points in common, but ROV is not fully inside Q. What do I do in this case? Let's check the code. So, given Q and a node V, starting when V is the root of the tree, if ROV is disjoint from Q, then I print no points in the tree or in the subtree rooted at V are inside the query disk. Recursively, just return nobody. If ROV is fully inside Q, then print or report all the points that are stored in any descendant node of V. Any node that are, if that's V, every node, every data point, not every leaf, but every data point that is stored in the subtree, you need to print it. Now, if I just want to know how many points there are in the query disk, then at this moment, I realize that the whole subtree of V is inside Q. I'll keep a counter here that keeps how many nodes I have in the how many data points I have in the subtree, and then just accumulate this number. Next, so ROV is partially overlapped with Q, or in this case, 2 subcases. If V is a leaf, like so, or like this one, well, it could be empty, or this leaf could have one data point, say A. Now, A might be the query disk or not. And that's the point that I need to explicitly check if the data point is inside the disk or not. But I know that the disk overlaps with quadrant, but I don't know if the data point is inside or outside. And that's where the number 17 comes from. All the points that are associated with the quadrant need to be checked individually inside the disk or not. So I balance how many points are there. Not a huge number. Else, V is not a leaf. V is not a leaf, but it overlaps with the query disk. What do? V doesn't put any more thoughts about its relationship with Q. Instead, it pushes the problem to its children. The idea is always make it your children's problem. So instead of reporting V and something, there's a V says, here is my northwest child with the same query disk. This quadrant, do the report. And do the report with my other child, my northeast child and my southeast. So I push the problem to all the 4 children, even though there could be children that don't have anything to do with Q. So the recursive call will just say, oh, that's Q and that's my region, they have nothing in common, I'm in this case, and just return nothing. And that's the simplest code to rearrange it. Again, Google for quad trees and applications and popularity of quad trees, and yeah, we'll see. Again, it's not the most efficient tree. It's not even the most efficient tree for one particular problem, but it's considered as a very good tree that can answer a lot of types of problems. Like if you tell me exactly what you are trying to solve, one specific type of problems, just ray shooting, maybe I can improve upon it. But sometimes you're doing ray shooting, sometimes you're inserting or deleting data, sometimes you want to ask what's in the data lies in some regions, and so on and so forth. So quad tree is like the 42. It's universal answer that fits to many applications. And again, why is this popular? Because implementing it is so simple. Really, really simple. Okay, to be continued.
I actually had a question about what your solution was for question 2 of the exam. I was hoping you could explain it to me.
Sure.